Dear students, let's discuss Poisson bracket. In classical mechanics, particularly in Hamiltonian formulation, we often need time evaluation of physical quantities like position, momentum, energy, and angular momentum uh, over time. That means we need time evaluation. Time evaluation of position, momentum, energy, angular momentum, etc. So what is meant by time evaluation? For example, if I throw a ball from here, eventually start from our hand to the ground. Okay. So in the way its height, speed, position change by second. So this is called time evaluation. So time evaluation is nothing but how physical quantities change with time. So then how this time evaluation can be done? So there is a mathematical formula. So for example, there is a function f, function of position, momentum, and time. So then time evaluation of this function f can be given by df by dt is equal to square bracket f comma h plus dou f by dou t. So this is how we find time evaluation of any particular function or a particle. Okay. Then here the important parameter is the bracket one. So that is square bracketed f and h. Here h is called Hamiltonian. H is nothing but Hamiltonian. That is energy of the system. Right. So describe time evaluation systematically. We introduce a powerful mathematical tool called Poisson bracket. So how to define Poisson bracket? How can we define a Poisson bracket? So let us say there are two functions f and g. So both are functions depending on generalized quantities, position, momentum, and time. Okay. So then Poisson bracket of f and g can be defined as square bracket of fg is equal to summation over dou f by dou qi into dou g by dou pi minus dou f by dou pi into dou g by dou qi. So this is how we define Poisson bracket. So it tells us how two quantities interconnected in phase space. How f comma g interconnected. In phase space. So essentially the Poisson bracket of the for example this Poisson bracket of f and h tells how f evaluates our system's dynamics. Note that if in this equation if Poisson bracket of f and h yields to 0, then we can say that f is conserved quantity. And also we can say f is a constant of motion. So a constant of motion. That means it don't change with respect to time. So this concept gives us a beautiful identification of conserved quantities and connect them with symmetries in the system. So in the essence, Poisson bracket describes dynamical interaction between the quantities. Describes dynamical interaction between quantities. They form foundation for classical mechanics and quantum mechanics. There were some canonical quantization. Okay. Now let us discuss some important properties of Poisson brackets. So important properties. Properties of Poisson bracket. So the first one is Poisson bracket of same parameter Qi and Qi is equal to 0. Similarly, Poisson bracket of Pi. What is Pi here? Momentum. And similarly, Qi is position. So Poisson bracket of same parameter will yield 0. And Poisson bracket of different parameters may change. Delta to j. It will be 0 if I is not equal to j and 1 if I is equal to j. Okay. And the second parameter property is antisymmetry. That means phi beta of g is equal minus into minus g comma f. That means interchange of the function reverses the sign of the bracket. So this is very important. The other thing is Leibniz rule. That means fg h equal f into g comma h plus g into f comma h. So here we have three functions f, g and h. So in that case we can write the Poisson bracket as a product rule. So Poisson brackets acts like derivative when applied to products, and also bilinearity. Example, if a is a constant, af plus bg comma h can be written as, we take it out the constant a outside, and similarly we take it out constant b outside. So like that we can write. And similarly, for example, h comma af plus bg.
Recondition. Okay.
A into h comma f plus e into h comma g. So Poisson brackets are linear in both arguments. Here a, b are constants. So now let us see some problems. So now let's see the first problem. Let f of qp is equal to sin of q and g of qp is equal p into cos of q. So now complete the Poisson bracket. So this is very simple problem. So we need to find Poisson bracket. So how it is defined? Dou f by dou q into dou g by dou p minus dou f by dou p into dou g by dou q. So first of all, we need to find these partial derivations individually. So remember, these are partial derivations only. So first of all, let's write dou f by dou q. So that means f the given function f, that is sine q, dou by dou q of sine q, which is nothing but cos q. So similarly, I find other things also. Then dou g by dou p will yield cos q, and dou f by dou p is equal to 0, and dou g by dou q is equal to minus p into sin q. So now we will substitute these all four quantities in this function. So then f comma g will become cos q into cos q minus 0 into minus p into sin q. So if we simplify it, you will get cos square q. So therefore, Poisson bracket of fg is cos square q. Now the second question is, so which of the following pairs have a vanishing Poisson bracket? So if you observe here, the first one is q comma qj. So I already told Poisson bracket of same parameter or same physical quantity will yield 0. So similarly, option B also 0, and option C definitely it will not yield 0. Of course, it depends on I, j values. So it is from this we can directly say A vanishes and B vanishes. If you observe D, so here D is q square j by pj. So it won't vanish. If you solve it using Poisson bracket formula, you can get somewhere like this. So definitely answers vanishing the terms are A and B. Now let us see the third one. So the next question is, let f is equal q square p and g is equal q p square. Find the Poisson bracket of fg. So again, we'll write the definition of Poisson bracket. F comma j is equal dou f by dou q, dou g by dou p minus dou f by dou p into dou g by dou q. So now we have the functions f is equal q square p and g is equal q p square. So now we substitute these values in these functions. We find individual partial derivations, and we again substitute them in the formula. So from this I can write directly, so dou f by dou q is equal to qp. So it's simple differentiation only. So dou g by dou p will yield to qp, and dou f by dou p nothing but q square. So then last one, dou g by dou q yield p square. Now just plug in these values in this, and simplifying, you will get f comma g is equal to qp into 2qp minus q square into p square. So if you simplify it, you will get 3q square p square. Now the first question, if c of qp is a conserved quantity and Poisson bracket of c with h is equal to 0, which of the following is necessarily true? So the first one is dc by dt is equal to 0, and Poisson bracket of hc is not equal to 0, c must be cyclic, and c does not depend on time. So if you remember the basic definition of time evaluation, given by dc by dt is equal to Poisson bracket of c comma h plus dou c by dou t. Okay, if actually given from the given data C comma H is equal to 0, then obviously dc by dt is also 0 if dc by partial differentiation of dou c by dou t is also 0. So that is C is not time dependent. C is not time dependent. So option A is correct. So if you observe option B, H comma C is equal to minus C comma H is 0 by antisymmetry. So this is false. So what about option C? So C must be cyclic, means it does not appear in the Hamiltonian. But C can be any function, not necessarily be a coordinate. For example, angular momentum. If you take angular momentum L, may be a conserved quantity, but not it is a cyclic. So it cannot be always true. Okay. Similarly, if say option D. So if C is not dependent on time, contradicts the requirement for the conservation. We typically demand that conservation quantities are independent of time. So this is also false. Okay. Now let's see the. So which of the following statement is correct regarding Poisson brackets? The first option is if Poisson bracket of f with h is 0, then f is necessarily constant. B, if f and g are constant of motion, then f comma g is 0. Third option, if c is conserved, it commutates with every other quantity. If d, f comma g is not equal to 0, f cannot be a symmetry of the system. So this is a bit of theoretical question. You have to think about it logically. So if you see the options, option A is not necessarily correct. Why? F is a constant along trajectories, but not necessarily a global constant. For example, if you take angular momentum satisfies LH is equal to 0, but LX is not a constant everywhere, right? So that's why option A is false. So if see option B, so this is like a trap. Even if f comma g are conserved, that means Poisson bracket of f comma h is equal to 0, and also Poisson bracket of g comma h is equal to 0. Their Poisson bracket, that means f of g, cannot be 0. Sometimes it may 0, but it's always not true. So that's why this is also not possible. For example, if you take commutators, angular momentum commutators, Lx, Ly will yield Lz, right? So all are conserved, but bracket is non-zero. So this is also false. So what about option C? So option C is also false. Why? Just because f is conserved does not mean it commutates with everything. With every parameter. Only with the Hamiltonian only it conserves. So this is also false. So what about option D? If f comma h not equal to 0, that means f changes in time. So it cannot generate a symmetry. So this is true. Non-zero bracket implies a change. So option D is correct. So we can find a PDF file of this explanation along with video. Please find that. Not only this PDF, there are so many PDFs available for free. You can join our Telegram channel. Thank you.